Okay, so welcome everyone. We're very happy to have Kevin Miller come speak this week. So Kevin is a postdoctoral fellow at the Open Institute at UT Austin, and he was previously a PhD student at UCLA with Andrea Bertozzi. And he's going to be talking to us about ensuring exploration and exploitation in graph-based active learning. So please, Kevin.
Great, thank you, Matt. And thank you to the organizers for the invitation to speak here. I'm excited to talk to you about some of this work here in graph-based active learning and how it relates to a couple of interesting applications, but more importantly, for my purposes here, talking about how there's a rich area of analysis to be done in this problem space. I want to recognize that there's going to be a number of works that with a couple of different collaborators, such as Jeff Calder from the University of Minnesota, Ryan Murray from North Carolina State, and then my PhD advisor, Andrea Bertozzi, and one of her PhD students on the application side. So to begin, I want to introduce this idea of what I'll call the low label rate case of machine learning. We live in a world right now that we are able to generate and produce a massive amount of data coming in different forms, whether that's medical imaging, medical smartwatch data, text, images. But I want to distinguish between two types of data, labeled and unlabeled, where labeled data will come in the form of inputs with their associated outputs or labels for a downstream machine learning task. And unlabeled data will just be the inputs themselves. For example, this lung X-ray on the top right, that I would consider the X-ray image itself to be the input, and the associated output would, for example, be classification of healthy, not healthy, COVID, not COVID. The main premise of what I'm going to talk about today is that for many applications of interest, while it's easy to collect the inputs, it's difficult and costly to get the labels or outputs for those associated inputs. And so as an overview of the different learning paradigms that are usually considered here in machine learning and how it fits into this, supervised learning would constitute just using the labeled data. And usually we're assuming you, in those cases, that you have a sufficient amount of the labeled data. So for example, here on the left, if the XY coordinates are the inputs, the outputs would be the associated classifications of blue squares and red stars. But as I said, in a number of applications, the amount of labeled data is quite small. And so a small amount of labeled data is shown maybe right here doesn't give you a good idea as to what the true ground truth function mapping from inputs to outputs actually is. Unsupervised learning is a paradigm wherein we're just using the inputs themselves and trying to learn oftentimes useful representations or glean insights about the geometric structure of the data set. So semi-supervised strikes a balance, if you will, leveraging both of the sources of data, the ample amount of unlabeled data and the sparse amount of labeled data, where we're combining ideas about the structure, the geometric structure of the data set, in addition to the observations of the underlying signal mapping from input to output. And so one of the useful paradigms in this is can be graph-based methods, and that's where the majority of my work has focused. But a complementary problem to semi-supervised learning is active learning, wherein we ask the question of, okay, wonderful, I've used both labeled and unlabeled data, but what if I was allowed to label a few more data points? This little yellow circle here over on the left, for example, choosing to label this point that's currently unlabeled, but if I were to know its label, would help me better identify what the ground truth function really looks like. And so my work has primarily focused on this active learning problem of trying to decide what makes good query points and how that interacts with the semi-supervised learning problem and improving the classification results of semi-supervised classifiers. So as an outline for the rest of my talk, I'm going to give a little bit more setup and background of where I'm coming from, the types of methods we're really talking about, and then give some motivation in the form of some successful applications that I worked on at the end of my PhD and recently, where these things have been quite useful using active learning. And then I'd like to highlight two recent projects where we've designed active learning methods that we can give provable guarantees as to the behavior of this active learning process. I'll dive a little more into that to explain that later. And then summarize and conclude. So the setup will look as follows. We've observed some labeled data in the form of input-output pairs xj's with the labels yj's for a small amount of these pairs, and then an ample amount of the unlabeled data, which has just the inputs xi's. By the set curly x, I'll denote the set of all the inputs, and yj's we'll be assuming this classification task. And so the yj's will be integers between 1 and capital C, where capital C is the a priori assumed number of classes in our classification task. Curly L will then denote the set of labeled inputs, and curly U the set of unlabeled inputs. Then we can phrase the semi-supervised learning problem as, given our currently labeled data L, can we accurately infer the labelings or classifications on the unlabeled data? And active learning is complementary to this and says, given our currently labeled data L, can we judiciously select a set of currently unlabeled points that once they are labeled will help to improve the output of our underlying semi-supervised classifier. And so there's this interplay between the semi-supervised and active learning problem that I think can be visualized in the following way. So this active learning process will iterate between the semi-supervised inference and query point selection and Oracle query and update. So here in the top left, given our currently labeled data, we propagate, influence, or infer classification of all the unlabeled data points. Then we compute what's called an acquisition function, which helps to quantify how useful it would be to label a currently unlabeled point, then select a query point based on these acquisition function values. And that constitutes what I'll call the query point selection. From there, we query an oracle, or in application, this is a human in the loop or domain expert, that once they receive this currently unlabeled point, this query point, they give us a label for that. We update the labeled data and then iterate back to the semi-supervised inference. So there's this intimate interplay between active learning and semi-supervised learning. As I'll be primarily focused on graph-based methods, this would fit into the framework in the following way, that on our set of unlabeled data points, we construct a similarity graph where all the inputs, both labeled and unlabeled, we construct a similarity graph where edges represent how similar points in input space are. And then with this discrete graph structure, we can learn decision boundaries that hopefully help represent clustering structure of our underlying data set. And so in this way, it can help regularize and improve our results here with the semi-supervised classification task. And as we'll be talking more about graphs, I want to set up some notation that will be common. So given the set of inputs X, we'll interpret this as a set of nodes of a similarity graph that can be identified by an edge weight matrix Wij, where the ijth entry of W represents the similarity between Xi and Xj. Now these edge weights will be non-negative. So 0 will correspond to inputs that are not similar, and positive weight will be, and large positive weight will represent inputs that are quite similar to each other. Then we can define the degree of a node Xi to be the sum of the edge weights connecting to Xi. And then the degree matrix would then be the diagonal matrix with the degrees along the diagonal. From this, we can define a family of graph Laplacian matrices, which are a discrete graph analog of the negative Laplace operator from partial differential equations. And here I've shown a combinatorial graph Laplacian, a symmetric normalized graph Laplacian, and a random walk graph Laplacian, which are three common matrices here in graph-based semi-supervised learning. And sort of for my purposes at this point of the introduction is that these graph Laplacians correspond to capturing clustering structure. What we're trying to do with the semi-supervised or graph-based semi-supervised classification task, oftentimes we're trying to identify what I'll call a node function U that maps from the set of nodes, maps from nodes to capital C dimensional outputs, where that C dimensional output will reflect a belief about the classification of the nodes. And so we're going to be trying to minimize over node functions according to certain conditions and loss functions, but using this graph Dirichlet energy term, which can be written in terms of an inner product with graph Laplacian matrix and this node function u, can also be viewed in a quadratic form. This is specifically what I'm writing here for the combinatorial graph Laplacian matrix. So this quadratic form of the graph Dirichlet energy term really highlights what's happening as we try to minimize the graph Dirichlet energy term over node functions. You can see here that as a sum over all pairwise interactions, the edge weight wij multiplied by the difference between the node function at xi versus xj. So this is going to encourage node functions to have outputs that are similar at points that are similar in the graph, where similarity is captured in the topology of the graph, where wij being greater than or equal to 0. So then we can define a number of different graph-based semi-supervised classification models. And the prototypical one that I'm going to work off of here today is the one that will take the following variational form. This has been referred to as label propagation, harmonic functions model, or Laplace learning. So this model, we're finding computing a node function u that minimizes the graph Dirichlet energy term, subject to the constraints that we fixed the label points, the labeled nodes to be the one-hot encodings of their labels. So recall that the yj's are integers between 1 and capital C. And so EYJ will be the standard basis vector with a 1 in the entry corresponding to the yjth entry. So then here, what we're doing is we're fixing the node function at the labeled nodes and then learning an interpolating function between those fixed node outputs, where the smoothness of the interpolating function is determined by the graph topology. This has intimate connections to what we'll call the continuum limit of the discrete graph based semi-supervised problem. And we'll dive a little bit more into this, but main point here is that there's intimate connections between this continuum limit PDE formulation of the graph-based problem and the discrete, where one is seen as the limit as you take an infinite number of nodes. But with that intro about graph-based methods and where I'm coming from, I wanted to mention here successful applications that gives some motivation for continuing to look into these problems and establishing a better theoretical foundation for graph-based active learning. These applications, the main point here is that in hyperspectral imagery, wherein we were trying to do pixel classification, for example, this image right here is a hyperspectral image in a remote part of the world, wherein we're trying to assess the water levels in these remote regions to see how climate has affected this and monitor this, because we can't get scientists out to these remote parts. And so the pixel classification task, also the image segmentation task with hyper or multispectral imagery, we have large data sets that are often quite noisy, and it's going to be quite intensive for a domain expert to go hand label each one of these pixels. And so combining active learning with semi-supervised methods, we can improve the speed at which we can get accurate classifications and do this monitoring in these remote locations. Also synthetic aperture radar data, wherein we're trying to take SAR images shown here sort of pixelated, and there's a lot of rich information about the geometric or the shape of the objects. And so for different defense applications, one is trying to identify what type of military vehicle is present in the image. And so this one's an image classification task. Now, I'm not going to go into too much detail about how one really applies these methods here for these specific applications, but my main point being that in these applications, we were able to achieve state-of-the-art accuracy as compared to supervised deep learning models, while only labeling a small percentage of the data set. So the trade-off here we're talking about is while there's off-the-shelf great powerful supervised learning algorithms with neural networks and other things like that, in many applications, we don't have a really large amount of labeled data to make those kinds of classifiers super useful. And so by leveraging both the structure of the unlabeled and labeled data here with graph-based methods, we've been able to come into these different applications and achieve really great performance while only labeling a small percentage of the data set. So with that, I'll get to the first project that I want to mention today, which is joint work with collaborator Jeff Calder from University of Minnesota. And what we did is we proposed a novel form of what I'll call uncertainty sampling. And then I provided guarantees about the explorative nature of these query points in the continuum limit counterpart of this graph-based semi-supervised classifier. So what do I mean by exploration and explorative nature of these query points? Well, this comes down to this balance between what I'll call exploration versus exploitation, which is a similarly named problem in reinforcement learning, if you've heard of that. It kind of comes down to trying to ask the question or answer the question, what characterizes informative query points? So I think this can be illustrated with the following little toy example. Imagine I have this square domain shown here on the left, where I only have two initially labeled points, a red point and a blue point. Let's say, for example, that my current classifier, given that's currently labeled data, draws just a vertical decision boundary between inferring everything on the right to be class red, everything on the left to be class blue. Exploitation would be characterized as selecting query points, shown here as a yellow dots, along the decision boundary of our current classifier. In a sense, exploiting what we believe to be the true ground truth decision boundaries. But this is just the current classifier's inference as to the true decision boundaries. Exploration, on the other hand, would be characterized as choosing query points that are more spread out over the extent of our data set, potentially farther away from the currently labeled points. In a sense, being more conservative about our belief about the current classifier and how whether it reflects the ground truth decision boundaries. This would be especially important if, for example, the ground truth boundaries made this checkerboard pattern here, where that initial current classifier is not even a coarse approximation to the ground truth decision boundaries. And so exploitation at this early stage would be catastrophic. You'd be myopically sampling over here in the bottom left or the left-hand side and completely missing the blue squares over on the right. And so this would lead to suboptimal results here in the active learning process. So exploration, on the other hand, would be better able to capture or more likely to be able to capture all these different checkerboard patterns here. So the point here is that in the low label rate case of active learning, it's imperative that we explore prior to exploiting. And so we want to design acquisition functions that will be guaranteed to explore prior to exploitation. So that leads me to my first example of an acquisition function, which is uncertainty sampling. And uncertainty sampling is sort of the de facto standard acquisition function used in active learning. And it follows the idea that you want to label points that your current classifier is most uncertain about. Now, depending on how you define uncertainty, you're going to get different measures or different acquisition functions. One of the most common uncertainty sampling criterion, though, is what's called minimum margin sampling, which is to choose to query points that are closest to your current classifier's decision boundaries, which is exactly what I characterized as exploitation. So while this can be catastrophically exploitative, and most active learning acquisition functions are designed to be better than this type of uncertainty sampling, there are some pros to this flavor of acquisition function. One, it's a simple idea. It's intuitive, but it's also computationally efficient. Recall that in the active learning process loop, we're iterating between the semi-supervised inference and then query point selection. So at each iteration, we have access to the updated semi-supervised classifier. And so in a sense, uncertainty sampling is the cheapest kind of acquisition function, since we already have access to the classifier and don't need to compute other auxiliary variables or quantities of interest. And so what we do is we propose an uncertainty sampling acquisition function that is guaranteed, or has mathematical guarantees about exploring clustering structure of our data set. So to introduce this uncertainty sampling, the specific type of uncertainty sampling is going to be paired with a semi-supervised classifier, graph-based semi-supervised classifier of the following form. And so this is what I'll call this Poisson-reweighted Laplace learning with tau decay. And so that prototypical example of Laplace learning that I showed at the beginning, this is an adaptation of that, where in this variational form we have here, the graph Dirichlet energy term now is reweighted by this reweighting Xi, where this Xi is highly reweighted near labeled points to ensure that this graph Dirichlet energy and the whole overall graph-based semi-supervised classification problem has a well-defined continuum limit model in the case of having these constraints at a finite set of points. I'll talk a little bit more about this in a sec. But so we've got this adapted, this reweighted graph Dirichlet energy term. And then here on the right, I have this, what I'll call a tau decay term. This is for a constant tau that's positive. This is actually going to encourage the solutions, these node function solutions, to decay as we go away from currently labeled points. So this is going to help us to control exploration versus exploitation with the following acquisition function. The acquisition function we define then is what we'll call this minimum norm, which uses this node function solution at each node and just takes the 2 norm of that vector of outputs. So the rationale here is that as we have non-zero tau, as tau is positive, we're encouraging decay of these node functions as you go away from labeled points. So that in regions of your data set where that are far away from labeled points, the 2 norm, each entry here should be quite small. And so then once we've chosen enough points to sort of give a coverage of our whole data set, i.e. once we've properly explored, then this 2 norm is going to be minimized in between points of oppositely labeled classes. So to illustrate this influence of tau, I like this little toy example. Imagine that we have 5 clusters shown here at the top left, where I've colored each one to represent the distinct clusters. And then here on the top right, I'm showing a ground truth classification of blue versus yellow. Now the 2 red stars in the 2nd and 4th clusters represent initially labeled points. So the idea is then here on the bottom, I'm plotting the node functions of this Poisson reweighted Laplace learning for different values of tau, where the x-axis is the first entry u1 at each x, and the y-axis is u2. So for tau equals 0, I have that all of the outputs actually lie along the simplex here. And I've color coordinated and markers corresponding to the different clusters up here. So the cyan cluster of points right here is represented, represents this middle cluster, and same for blue, green, violet, and orange. So when tau equals 0, all the points actually lie here on the simplex. And so minimizing the 2 norm would select points here in the middle of the simplex, which is going to correspond here to this cyan cluster. What you get then is when tau equals 0, in this case, our sequence of choices, the query points, is essentially going to bisect in between points of oppositely labeled, points. But the problem is, in that case, we would completely miss the outermost clusters here on the left and here on the right, the blue and the orange clusters. They wouldn't have this minimum 2 norm. But when tau is positive, as you increase tau, you see here that the orange and the blue clusters are pulled in towards the origin, which reflects the whole effect of tau causing the node function solutions to decay. So as those are brought out, you can then see that the 2 norm would better identify that we need to explore these outermost regions prior to exploiting here in the middle of the simplex. So here illustrates that with this tau parameter, we can kind of control the exploration versus exploitation behavior of this minimum norm acquisition function. So now, as we get to our theoretical results, I want to introduce the idea of these random geometric graphs. The idea is that our discrete graph is going to be seen as a sample from an underlying data generating distribution. So those nodes, those inputs in our d-dimensional space are going to, we're assuming that they are coming independently and identically distributed according to an underlying density rho, where the clustering structure of the discrete graph is then going to be captured in the clustering properties of this underlying density rho. For example, here in 1D, I've just shown a mixture of 3 different Gaussians in gray, and then a sample of 100 points shown along the x-axis here as these x's. You can see that in regions where the density rho is larger, I have a higher concentration of x's, of samples. And so constructing a similarity graph from the set of inputs here, we would get more connected and tightly clustered clusters of points in these regions of rho that where the density is larger. So we can reflect clustering structure in this density rho, and then our analysis can say can consider the density rho. So we've got the similarity graph constructed from a finite sample from the underlying density rho. Then as we scale the edge weights properly, you're able to consider taking an infinite number of samples from the density rho. Now, there's a lot of details that go into showing this discrete to continuum limit convergence, a lot of really interesting details and careful work that needs to be done. But for my purposes here, it's important to say that the counterpart of this discrete graph Gaussian in the discrete case is a diffusion operator that takes into account this density rho. And for our purposes here with the Poisson reweighted Laplace learning, the whole point of that reweighting C is to ensure that we have a well-defined continuum limit model in the case of having a finite amount of labeled data points. And so our exploration guarantees will look as follows, with a cute little picture over here, I guess. So we're going to assume that the clustering structure takes the following form, that we have an open bounded domain omega in d-dimensional Euclidean space, that we have a set of disjoint clusters shown as these omega i's, wherein these omega i's are going to be clusters or regions wherein the density rho is relatively large. And they're going to be separated by a background region wherein the density rho is relatively small, shown here as rho of x is less than or equal to delta. Then with labeled sets LK representing inputs that we've seen labels of class K for, the continuum limit analog of the discrete graph-based Poisson reweighted Laplace learning model corresponds to a system of partial differential equations with this second order elliptic governing equation here with these boundary conditions, or fixing the labels at these labeled points according to whether or not the labeled point was of class K or not. So with these solutions UK, with the capital C different solutions to this system here, for the system of PDEs that you get for the different one versus all encodings of the labeled points, we then are considering the vector of outputs at each point in the domain. And so then the acquisition function here will be the 2 norm of that vector. So the idea of the analysis is then going to be that for a subset of the clusters, we're going to assume we have labeled points, shown here as a red dot, a blue dot. But then there's going to be an unlabeled cluster we'll call D. And we want to show that the acquisition function is small in this unlabeled cluster, and then large when you're close to labeled points. And so that's summarized in the following theorem. Like given this clusterability assumption on the data generating distribution density rho, and for tau sufficiently large, we can upper bound the acquisition function on the unlabeled cluster with this exponential bound here in terms of tau and delta, where delta is that sort of the magnitude, the largest magnitude of the density in the background region, also dependent on the distance to labeled points or clusters that have label points in them. So if the background density is really small, so if delta is small, then this upper bound is significantly improved. But then also we have a lower bound in balls of radius r around the labeled points, where these balls of radius r correspond to how large of a ball of radius r you can fit into the cluster, so that you have a relatively large value of rho in there. So by comparing these two, we can see this straightforward relationship of how tau controls exploration. So that when tau is sufficiently large, we will explore clusters, these unexplored clusters, prior to querying close to already labeled points. So for tau large, or relatively large, we get exploration. For tau small, we get exploitation. We can combine this into giving a sampling complexity result, quantifying how many points I'd need to choose in order to ensure that I've explored all my clusters. And this straightforwardly relates to the geometry of your clusters. The idea is that for properly chosen tau, we can ensure exploration of capital K clusters in big O of K queries, where the constant in the big O of K relates to the number of R/2 balls that you'd be able to fit into the already labeled clusters. So while this doesn't say we are guaranteed that the very next point we choose will be in an unlabeled cluster, it gives a more general sort of idea that what points you choose are inherently dependent on the geometry of the clusters. Notice we haven't said that the clusters are of a specific shape or size or how they relate exactly to each other. And this is in contrast to a number of other clustering assumptions that have been given in graph-based active learning, which do make these sort of restrictive guarantees. So in this more general setting, it's maybe not surprising that it's not a guarantee that you will choose your next query point in an unlabeled cluster, but in many ways, it's a more satisfying kind of result in that it's more general to this more general type of clustering structure. And so with this, wanted to see if we could validate the performance of this acquisition function in an experimental setup, wherein we need to be able to identify that exploration of clusters has happened. And so I created an experimental test bed. This isn't a standard test bed. This was just one that we came up with to try and validate the explorative capabilities of an acquisition function by taking the MNIST, fashion MNIST, and emNIST data sets, which are handwritten digits, letters, but then also fashion MNIST being pictures of different classes of clothing. So we interpreted the ground truth classes as clusters in an auxiliary classification problem, where you take, for example, with MNIST, take the digit mod 3 and assign that new value to be the new class of that cluster. So digits 0, 3, 6, and 9 would belong to class 0, 1, 4, 7 to class 1, and 2, 5, 8 to class 2. So then what we can do is we can see if I start with one initially labeled point per class, I'm only starting with a subset of the clusters having been labeled. So then as I go throughout my active learning process, I can monitor not only accuracy as a function of active learning iteration, but also the proportion of clusters that have been sampled from as a function of active learning iteration. And so results like that can be shown or look as follows. Here on the left, I'm showing an accuracy plot, where on the x-axis, I'm showing the size of the labeled set, also corresponding to active learning iteration. And on the y-axis, we have the accuracy on of the semi-supervised class on the classification task on the unlabeled data. So our method is shown as blue dots and these gold triangles, as well as some other acquisition functions. While it's a little bit muddled here, you can see the gold and the blue curves here increase fastest and level off at a higher overall accuracy than other methods, showing, demonstrating that it was efficient. The sequence of choices of query points chosen by this minimum norm uncertainty sampling led to greater increases in accuracy and also getting to a better, higher overall accuracy, suggesting that these were useful query points. But even further, I can see that this acquisition function was efficient at exploring the clustering structure. Because over here on the right, I'm showing, as a function of active learning iteration, what fraction of clusters have been sampled from. So you see here, the gold and the blue have reached 100%, or a fraction of 1 of all the clusters being sampled from within 10 iterations. So these are results averaged over 10 different trials. And so this shows that in every single trial, it took only 10 iterations to have ensured that we've sampled from every single one of the ground truth clusters. And this is superior to the other methods that we compared against. So similarly, see similar results for fashion MNIST as well as the MNIST datasets. So this was exciting to see that we could give a simple, computationally efficient acquisition function that we could give theoretical guarantees that will explore the clustering structure and see that these choices did indeed lead to good results here in the numerics.
Kevin,
so with
can I
that,
ask a quick question?
For sure, yes, please.
So on the previous slide, the tau going to 0, can you explain what's that's about?
Great, that's a great question. So the blue was just keeping tau positive and fixed, and the gold is starting tau positive and then sending it to 0. And that was trying to reflect that what we saw in smaller examples, in like 2 dimensions, that you needed to send tau going to 0 to ensure that you really get to efficient exploitation after you've explored. So if I go back maybe to this case right here, once I've selected a point in the orange cluster and the blue cluster, and then once I've selected points in each one of the clusters, I really want to start sampling in between the clusters to identify the decision boundaries. And so what we saw in examples and tests with here in lower dimensions, that you needed to send tau to 0 to really be more efficient at, after exploring, getting down to the decision boundaries. But what was interesting, or maybe a little surprising to us, was that in these larger data sets, or higher dimensional, I mean, not the most high dimensional, but relatively high dimensional for us, we didn't see much of a difference between sending tau to 0 and keeping tau constant. And so the actual choice of tau, how large to make it and how to send it to 0, is still an open problem and an interesting question. But that's the difference between the gold and the blue. Does that answer your question?
Yes, it says. But I guess a follow-up question is in these experiments, how did you choose tau going to 0?
Right. So the tau going to 0 was just a heuristic. It was saying that I give a certain number of iterations, a certain number of query choices that I want to have started, a decay schedule. So I start at a certain value of tau that I've chosen to be, that I chose here for the blue experiment. And then I just say within 20 iterations, I want to have to be within basically a tau equals to 0. And so then I'm just a geometric sort of multiplying by a certain rate at each iteration to decrease tau. So it was just a hacky thing that we tried. And it did very well in the smaller experiments, but here in the larger experiments, it didn't seem to provide much of a benefit. So.
Okay, thanks.
Yeah. So the next work I want to talk about is what we're calling Dirichlet learning for active learning. This is joint work with my collaborator Ryan Murray at NC State. And the main point I want to give here is that we propose this new semi-supervised classifier that has this nice Bayesian formulation for these graph-based semi-supervised learning models. And it more of a specifically tailored to classification. And what comes along with that setup then is actually a straightforward and cheap acquisition function that will turn out to be a form of uncertainty sampling, but looks a little different than the previous uncertainty sampling criterions that I talked about previously. And we've done analysis to provide exploration guarantees under a different clustering assumption, but then also trying to take a step towards giving an analysis of exploitation. And that we've provided some steps, but there's still a lot of work to be done on the theoretical foundations of analyzing exploitation in these graph-based active learning methods. So to motivate where I'm coming from, a lot of various graph-based semi-supervised classifiers were phrased from a probabilistic perspective as instances of Gaussian random fields or Markov random fields, wherein the correlation structure between the random variables is reflected in the structure of the graph Laplacian matrix. So then you can view that the node function we're learning from the variational form as the map estimator of an underlying posterior distribution, a maximum a posteriori estimate of an underlying posterior distribution. For example, here I'm showing an objective function corresponding to a graph-based semi-supervised learning model that's related to the harmonic functions, the Laplace learning model I mentioned. But now instead of hard constraints at the labeled points, I've encapsulated it here in this fidelity term, a loss function, where the loss function L is like your usual empirical risk loss for in supervised learning. But so this loss function encourages node function outputs to be close to the labels that we've seen. So I could view this, the minimizer of this objective function, assuming that it's all convex, as the map estimator of a corresponding posterior distribution that factors into a prior that corresponds to the graph Dirichlet energy term and a likelihood that corresponds to the loss term here. So if the loss function was a mean squared error, then we'd actually have that the posterior distribution would be Gaussian because the prior and the likelihood both correspond to Gaussian distributions. So while this is really interesting and allows one to create active learning acquisition functions that relate to the variance and other statistical measures of the corresponding posterior distribution, in this current form, it's inherently a regression model, not a classification model. And so we introduce this idea of what we'll call Dirichlet learning to present maybe a more Bayesian classification type of framework for these semi-supervised classification models. So the idea is that we can define a categorical random variable, y, at a node x. So this categorical random variable will be influenced by probabilities, P1 through P capital C, which then we're going to place a distribution over these random vectors P, where P of x is the vector of P1 through P capital C at the node x. And this Dirichlet random variable will be, P of x will have concentration hyperparameter alpha. So our belief about P of x, which influences the classification of x, is determined by these concentration hyperparameters. So the nice thing about this is that with properties of Bayesian conjugacy of these Dirichlet random variables, if we observe a sample from a category K, then it just corresponds to a simple update of the concentration hyperparameter that then is the update as to the posterior belief about your probabilities in the random vector P of x. So summarizing here, in this more classical Bayesian framework, given a concentration hyperparameter alpha that determines our belief about the probabilities, we can then get our belief about the categories, the actual classification of a point. So then with observations, we can update those probabilities by updating the concentration hyperparameters. Now, usually these observations are integer valued. We think of things like coin flipping and in the case of beta random variables, where it's just binary 0 or 1 and success versus failure. And so seeing a heads would correspond an integer value of 1 as an observation, or failure, also integer valued. But our variant is going to consider observations that come from propagating what we'll call pseudo-label from the labeled set. So these will be continuously valued occurrences or observations where we've propagated what we'll call pseudo-label. So, and I'll explain that in just a sec, but the idea is then bringing all of these Dirichlet random variables together, we get a Dirichlet random field. So each of the random vectors, P of X, are Dirichlet random variables, each identified by their own concentration hyperparameter. So we update the alphas according to the amount of pseudo-label propagated from labeled data to the node X. So the idea here is that for with each of these labeled sets, LK, we propagate, or we take the sum of all these propagations from the labeled points in the labeled sets to the point in question. So for X in our graph, we take the sum over all of the similarities, these propagations from labeled points of class 1 to the unlabeled point X, and do the same thing for each of the other classes. In order to have a nice well-defined prior and posterior, we add a uniform prior across here, which doesn't change the classification, but just makes the analysis sort of nice. So these propagation operators, what am I thinking about with all of that? Thinking about how to propagate influence from a source point. And my case that I'd like to make is that graph-based propagation operators can be especially useful as a tool for capturing similarity, as they can capture clustering structure, also reflected in the density of the underlying data generated distribution. So in the interest of time, I'll just gloss over this and say that the heat maps I'm showing here are bright in regions that are similar to the point in question, shown as a red X. And you see for what will be the graph-based and the continuum limit counterpart of the graph-based, we have that there's higher similarity inside of the clusters as opposed to radially symmetric propagation operators or kernels. And so this leads to just the summary of Dirichlet learning being Dirichlet random field with a uniform prior over prior belief about the probabilities. We update those probabilities according to the pseudo-label propagations, and that then reflects our belief about the classification of the points in the graph. And then finally, we can get the mean estimator, use the mean estimator of the random vector P. So this P hat sub K is the kth entry of the mean estimator, which has this nice closed form solution, which then allows us to say, we infer the label of a point to be the index of the maximal entry of the mean estimator, here shown as y hat of X equals the argmax of P hat K. So due to the simple form of this mean estimator, this is simply identified by the index of the maximal entry of the concentration parameter alpha. So our alphas completely determine our classification. And because we have this nice Bayesian formulation of these random variables and this classification task, I have a straightforward way of quantifying uncertainty in the classification at a point. And one of the ways of doing that is taking the trace of the covariance matrix of the random vector P of X. So given our currently labeled data, what is the belief about the random variable P of X, and take the trace of that covariance matrix. The idea here really is that this is a straightforward measure of uncertainty. And since it's only a function of the classifier at each iteration, I can call this an uncertainty sampling criterion. And so it's going to be cheap to compute. So we'll call this the Dirichlet variance acquisition function. And so that will be the trace of these covariance matrices shown here as just V of alpha of X. I see we're running out of time. I'll end with this slide, which is showing that our theory, we assume that showing exploration comes down to, we assume that we have a mixture model where our density rho is a sum of these class conditional distributions weighted by these marginal class marginals weights here. And we define the idea of a sigma delta epsilon class separator, which is the idea that a propagation operator can properly separate a mixture model if from this mixture model we get these disjoint sets where the class conditional distributions on the sets omega I are relatively large, like they're primarily supported on the clusters, and that for points in the same cluster, the propagation operator between the two is large, so delta will be close to 1, and it'll be small between points in opposite clusters. This reflects the idea that kappa, this kernel, or its propagation operator, is able to distinguish between clusters of the mixture model. And one of the main motivating examples for us is work by Franca and Nicolas Garcia Trios and Bamdad Hosseini in 2021, in which they introduced for a mixture model this notion of a well-clustered mixture model. And whereas they're analyzing continuum limit of spectral clustering, we can use this type of well-clustered mixture model that then leads to showing that graph-based propagation operators that correspond to the continuum limit of these Graph-Gaussian, these graph-based propagations, is an especially good sigma delta epsilon class separator of that well-clustered row. We're able to give guarantees from that, but maybe Matt, I think I'll stop right there just to leave time for some questions. I apologize.
Okay, thank you very much, Kevin. That's a very nice talk. Right, I'm just going to stop the recording.